Hello, my name is Kevin Sloat, and this is my paper with Elaine Lee. The problem we were trying to solve in our paper is how do we measure model performance on unlabeled data? So to solve this issue for our business leaders, a colleague and I, Elaine Lee, we developed a solution to estimate the error rates of models in production without relying on any ground truth data. And to do this, we drew inspiration from the field of epidemiology. We drew inspiration from the field of epidemiology, where research was done to estimate the efficacy of diagnostic tests in unknown distributions and populations of data. Here, instead of diagnostic tests, we just replaced the diagnostic test with machine learning binary classifiers. By looking at the probability of each cell count and then relating it to what it must be in terms of the true positive rate and true negative rate of each classifier, we get this formula of equations. The next component of our solution is we separate the tests over two populations of data. So if you have theta 1 and theta 2, which are the prevalence of the diseases in two populations, suddenly we have this system of equations that we can solve with something simple like a maximum likelihood estimate, or we could also do Gibbs sampling. In our paper, we eventually applied Gibbs sampling to do a higher dimension of populations and categorizations. So what we're doing is we're taking our data, we're splitting it into two populations. Either we have two populations naturally, like two data centers, and we're going to estimate the metrics of false positive rate and false negative rate. In this situation where it's impossible to measure them. So once we have this 2x2 contingency table, we can do this estimation. And this appeared in this paper, the Huey-Walter paper, where they're estimating the error rates of diagnostic tests. This appeared in 1980 in an epidemiology paper. So in the simplest case, where we just have the two categorizations, we want to formulate the maximum likelihood estimate. And the maximum likelihood estimate is giving us this parameter vector. And the parameter vector has all the error rates that we want to estimate. And then we also get formulas for the covariance and the information matrix. And this method, like I said, generalizes to n by m by k dimensions of categorizations and populations and diagnostic tests. And to solve this bigger use case, we applied Gibbs sampling, not just maximum likelihood estimate. So concretely, we don't want to just do this for data that is stagnant. We have a bunch of data coming in, and we separated the data into two populations, and then we manually wrote out what each one of the parameters would be given the observations of all the tables. So we managed to produce this online algorithm to calculate the model performance. And what you do is you initialize the model, and you have these counts, and then each iteration of data accepts a new count for one of the entries of that contingency table, and then as the cell counts update, we calculate the parameter vector of interest, which gave us our solution. So now when there's situations where you don't have two populations of data, we also explored latent class analysis. And latent class analysis is a subvariate of the LPA analysis, and it's designed for categorical variables. So we're uncovering the latent classes of categorical variables instead of continuous variables, because our diagnostic tests or machine learning models are actually doing yes/no predictions. So those categorical variables are partitioned into two latent classes. So now, just to briefly summarize our results, We started this on the Wisconsin breast cancer data set, and this is a publicly available data set for cancer diagnosis. This is a publicly available data set for breast cancer diagnosis. There's 30 numerical attributes that are derived from biopsies. The label of the breast cancer biopsies is either benign or malignant, and they either have breast cancer or they don't. And this is a very common data set in machine learning, and some of the features of the biopsy results are the radius, the texture, the perimeter, the area, the smoothness, compactness, the concavity, the symmetry, and there's a few more. So because we couldn't reveal our customer data to show how well this was working, we partitioned the Wisconsin breast cancer data into 2 latent classes. And this is an example of the 5 features we chose, and we did the latent class analysis to show that it nicely partitioned into two classes, or 2 latent populations. Then we applied our machine learning models, and we categorized them according to either malignant or benign on our 2 populations, and these are all the counts of our categorization engines. And then what we did was we applied the Huey-Walter method, and then we approximated what the true positive rate, true negative rate, and the other performance metrics would be based on our estimate from Gibbs sampling, and then we compared it to the true values. And we found that over iterations of this data, we found that the true values were very, very close to what the Huey-Walter method was estimating. So that's a rundown of our method, and this applies to additional data sets. Our key reference is Huey-Walter and estimating error rates. And you can check out our